Okay. So I'll just share my screen. So yeah, turn off. Yeah, I'm sharing my screen. Just 1 minute. Okay, I'll turn off. I'll turn it. One. Okay. So I want to be doing it on degree sequences of graphs. So first I'll define a graph. So here's some notation. If X is any set, we denote the set X choose 2 by be the set of all one element and two element subsets of X. Okay. So a finite graph G is a pair. I mean, there are many definitions for a graph, but I like this definition the best. So a finite graph G is a pair V comma phi, where V is a finite set and phi is the function from V choose 2 to the to non-negative integers. Now one can visualize a finite graph as a finite set of vertices in a plane with edges connected between those vertices. So the function phi actually determines the number of edges between the two vertices. So if phi is, for example, if phi of two elements is of one two element subset is 2, then there'll be two edges between those 2 points, like that. Okay. So let G equal V phi be a finite graph. We define the degree of a vertex V denoted by dV. So a vertex is basically an element of capital Oh, I sorry for that. Namely, the handshaking lemma. So it basically says a sum of all degrees over all vertices is going to be twice times the number of edges. This is a fairly standard result. Oh, I'm not going to prove any result here just because we have limited time. So yeah. Okay. So by the handshaking lemma, we require summation di to be even for it to be a degree sequence of some graph. It happens that this necessary condition also happens to be sufficient. So this sequence is a degree sequence of some graph if and only if its summation is even. And I mean, this problem is way too easy. So general finite graphs can have loops, which was over here. V4 has a loop. The edge F is a loop, and there's something called multiple edges, which is two different edges connecting the same two vertices. Sorry, there should be W here. To be precise, a finite simple graph is a finite graph where this basically encapsulates the multiple edge thing. I mean, they can't be two two edges between the same between two vertices, and also for any one element subset there are no loops. Basically, there's no edge that connects it to itself. So this is the definition for a simple graph. Okay, so a weakly decreasing sequence is d1 to dk or up to dk is graphic if it is a degree sequence of a simple graph. The graph realization problem is determining whether a given sequence is graphic or not. So we want to find a necessary and sufficient condition for graphic sequences. So there's a theorem proved by Paul Etersch and Galai, and the theorem is that this sequence d1 up to dk is graphic if and only if summation di is even and there's this condition: summation di is greater than or equal to j times g minus 1 plus this another summation di min di j I going from j plus 1 to k, and this holds for every j between 1 and k. So basically you will have k inequalities and each inequality should hold. If each inequality holds, then this is graphic. That means, I mean, these numbers are the degrees of some graph, vertex degrees of some graph. Okay, now the Havel-Hakimi algorithm. Sometimes we want algorithms to determine whether a thing has property P. So algorithms actually are much faster than checking general theorems. So the Havel-Hakimi algorithm is a recursive algorithm for actually deciding whether a sequence is graphic or not. So this basically says is that this a sequence is graphic if and only if some altered sequence is also graphic. So how do this altered sequence is basically you remove d1 and then you subtract 1 from the next d1 largest numbers. So for a one vertex graph, the only simple graph is the isolated vertex, obviously. So that has degree sequence 0 because I mean there's no edge connected to that. Hence, all graphic sequences terminate at 0 with repeated iteration of the algorithm. But for example, consider sequence 4 4 2 2 2 1 1. So one iteration would give us, so 4, we remove d1, which is 4, and then the next four largest element numbers will be 4 2 2 2. So we subtract 1 from these four elements, we get 3 1 1 1, and these 1 1 come over here. So a computer can basically how can this work is that a computer can store all memory of all graphic sequences of length k, and then for length k plus 1 it can just do one iteration and then check if that new sequence will be graphic. XW get added. So one can actually prove that the degree sequence is invariant under a two-switch transformation. And in fact, we actually have this result. Two simple graphs have the same degree sequence if and only if G can be transformed into H via a sequence of two-switch transformations. So we'll do the same thing for digraph. So a digraph is basically, it's a similar thing. Instead of doing B choose 2, we just do the Cartesian product B cross B. The domain will be that. So for visualizing digraphs, you can think of the edges being directed from one end is an arrow from one end to the other end. Okay. So the simple digraph is basically where there's no loops. This is a loop right here, and multiple edges or arcs, you can call them. Yeah. So in degree of a vertex is basically the number of edges that are directed into that vertex, and the out degree something is the number of edges that are directed out of V. So for example, if we over here we have d minus 3 is 4 because there's this edge, I hope you can see my mouse, this edge, this edge, this edge, and this loop also is coming into a 3. So d minus 3 is 4 and d plus 3 will be 1 because one edge that out of 3. Okay. So an analog of the handshaking lemma for digraphs is this: the summation of all the in degrees equals the summation of all the out degrees. So there's also an analog of what I said in slide 4. So in slide 4, it was this: if a sequence is a degree sequence of subgraph, if only if this is even. So in the same way, you can think of this is a realizable as degree pairs of a digraph if only if like the in degrees equal the summation of the out. So summation ai equals summation bi, and you want ai to be the in degrees and bi to be the out degrees. Okay. So we like to solve a digraph. We would like to solve a digraph realization problem. So we want to find if we are given a sequence of pairs of normal. I thought I could finish it without any proofs. I think. Okay, so um, of non bears of a it should be actually a simple digraph. I'm sorry for that. So we will first need to apply a graph transformation. So a bipartite graph is basically a graph where you have two partite sets and one edge goes from one partite set to the other partite set. This is and the split of a digraph is with what you do is you have two partite sets, and for each vertex v there's exact, so it's two copies of v minus and v plus, and for each there are two copies of each vertex, x minus and x plus, and u plus is connected to v minus if only if there's an edge in the diagram that goes out of u and into v. And you can check that this occurs, d plus minus v equals d v plus minus, and the fact that the split of a simple diagram will be a simple bipartite graph. We now want to find a test that's to say that whether p1 to pk and q1 to ql is bigraphic. That basically means that pi are the degrees of one partite set and qi are the degrees of the other partite set. So here's a result that is similar to Havel Hakimi. Basically, what you do is you remove P1 and then you subtract one from Qi, the P1 largest elements from Qi. So if this is your Pi and this is your Qi, over here you remove the P1, which is 4, and then the largest 4 elements you subtract 1. So I've done that here, and these two ones just get carried over. So uh, to I would like to actually know more about degree sequences and for other types of graphs. So like graphs with chromatic number k, graphs that are k connected, kh connected, planar graphs, and etc. So also I would also like to do an enumeration from given a degree sequence, how many simple graphs are there uh, that have the degree sequence. And this is my sources and citation. So yeah, thank you. Yeah.
Good evening, sir. Good evening, sir. Okay. Sir, are you able to see my screen? Sir, are you able to see my screen?
Oh yes, we can see.
Okay, sir. Actually, my topic for the research project is the Riemann hypothesis, sir. Just to give a catchy headline, I have written that this how to win $1 million in number theory. Yes, sir. No, no, sir. I started this. I have opened the presentation actually. Sir, can you see now? So let me present one more time.
No, sir, I stopped the games.
So now can
Yes.
everyone see the presentation? Yes, sir. So now everyone can see. Okay. So the topic for my yes, sir. The topic for my is the Riemann hypothesis, sir. And I have just for the catchy, just for getting looking like the headline should be catchy. I've written that how to win $1 million in number six. This problem was yes, yes. Okay. So actually, I'm presenting about the Riemann hypothesis, which was proposed by George Frederick Bernard Riemann. I will start with the history and introduction. In the year 2000, the Clay Mathematics Institute offered a prize of 1 million US dollars for the solution of each of these seven famous problems. Actually, one of these were solved by the Poincare conjecture was one of them, which was solved by Gregory Perelman. Riemann hypothesis was one of these million problems, and experts have been trying to prove it for more than 150 years. So, what is Riemann hypothesis, and why is it important? The problem is concerned with the distribution of prime numbers and was introduced by Bernard Riemann, a German mathematician who died at the early age of 39, while a professor at Göttingen University, where he had followed the footsteps of Gauss and Rushdie. Elected to the Berlin Academy in 1959, Riemann expressed his gratitude by presenting his only paper in number theory. This was the first page of his research paper. It consists of 8 pages, and this was the first one. Now, before I present the Riemann hypothesis, I need to tell a bit about the infinite series and complex number. The series, we'll start with the this series: 1 plus half plus 1 by 4 plus 1 by 8 plus 1 by 16 and so on, where the denominators are the powers of 2, and this series continues forever. Now we can solve this series using this diagram and see that this is the 1 cross 1 square, and we can see that this series converges to 2 because this part of the series converges to 1, and 1 plus 1 is 2. The same way we can generalize this result to show that this infinite series of the form 1 plus 1 by p plus 1 by p square plus 1 by p cube converges to p divided by p minus 1. But not all the infinite series converge. A celebrated example is so-called the harmonic series. It is like of the form 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 and so on, whose denominator are positive integers. To see why doesn't it have a finite sum, we'll group the terms as 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5 plus 1 by 6 and so on. Now this sum is larger than the following sum: 1 plus half plus 1 by 4, 2 times 1 by 8, 4 times 1 by 16, 8 times and so on, which equals to 1 plus half plus half plus half, because each group has the sum half, thus the series diverges to infinity. Now this is the graph of this sum. As you can see, this diverges to infinity, and the Euler proved that in 1737, if we throw out most of the terms from this series and leave only those whose denominator are prime, that is 1 plus 1 by half plus 1 by third plus 1 by 5, here all that in the denominator they are prime numbers, then there is still no finite sum. Now we'll know about the zeta function. In the early 18th century, there was a challenge to find the sum of this infinite series. This was the infinite series, and it was known as the Bessel problem. Euler proved that this infinite series converges to pi square over 6, and proudly said that quite unexpectedly, I have found an elegant formula involving the quadrature of a circle. In the same way, he proved that when the denominators are the 4th powers, then the sum is pi square, pi raised to the power 4 divided by 90. When the denominator is of 6th power, then the sum is pi raised to the power 6 over 945. And he continued this calculation till 26th power and calculated it as this, as you can see this, a big, huge number. And he didn't stop here. He generalized this series and for the nth and denoted this as the zeta function, where this is the Greek letter. and written as zeta of s is summation from 1 to infinity of the function 1 over n to the power x. Now, although the zeta functions seem to have nothing common with the primes, but Euler spotted a crucial connection. And this connection was that the zeta function, which is this one, according to the definition of Euler, we can write it as a product of primes. Right? As you can see, 2, 3, 5, 7, 11, and so on. These all are primes. And we can write this in this form also. And this remarkable result is called the Euler's product and provide an unexpected link between the zeta function and all the prime numbers. This connection can be used to give another proof that the list of prime is never ending. Now, complex number. Before I present the Riemann hypothesis, I'll also need to present the idea of a complex number. A complex number is a symbol of the form x plus iy, where x is called the real part and y is called the imaginary part. Examples are 4 plus 3i, 2i, and 3. 3 can be also thought of 3 plus 0i. These points are represented in the Argand plane. We can show that this point is 4 plus 3i. This point is 3 plus 0i. And this point is 2i. And instead of the y-axis, this is called the imaginary axis, and this is the real axis. We had discussed a little bit about complex number because the Riemann hypothesis is defined for a complex number as the input values of the zeta function. Now, we'll study Riemann hypothesis in three cases. First, when the real part of the zeta function is greater than 1. Second, the real part is less than 0. And the third part, when it lies between 0 and 1, which is actually related to Riemann hypothesis. In particular, we discuss about the zeros of zeta. In case 1, first I'll prove that the for real part is greater than 1, then the series is diverging. We let the zeta function as this by definition of Euler, where now the s is x plus iy. And we can write 1 over this function as 1 over n to the power x into 1 to the power n into y, and write this as in this form using the complex exponent that a to the power iy equals to e to the power iy into, actually here it is e to the power I into the natural log of a. Natural log of a. And theta is y times the natural log of a. And as I modulus of e raised to power I theta is 1 for any value of theta, therefore this can be written as 1 over n to the power x. And from the using integral test, we can get this limit. And we can see here that this integral converges only when x is not equals to 1, as you can see here. And will converge only when this part is this one is great in this minus x plus 1 is less than 0, actually. Then this implies that x is greater than 1. Then we can say that the series converges for real part of s greater than 1. Now, we are discussing the case for the real part greater than 1, we can write this is by the definition of the function by Euler, and this is also the Euler's product. We can write this in this form. And then we can say that for getting the zeros, we can say that e to the power s equals to 0. Not- Okay. And we can see that there are no zeros in this case. And when case 2, when the real part of 0 is less, real part of the zeta function less than 0, then we define the zeta function as this functional equation. And for the zeta to be 0, the sine phi s should be 0. And using that sine, if sine theta is 0, then theta is n pi. Then we can write this as pi s by 2 equals to n pi. This implies s equals to 2 9, where n belongs to the integer. And hence we can see the trivial zeros, which are called trivial zeros of the zeta function, which are minus 2, minus 4, minus 6, minus 8, minus 10. Now comes the statement of the Riemann hypothesis that if the real part lies between 0 and 1, And Riemann stated that the non-trivial zeros of the Riemann zeta function have the real part as half, where that is the zeta of half over it is zero, where t is a complex number. And this is the critical state where all it is the Riemann said that the all conjectured that all the zeros of the zeta function lies in this state with the real part as 1. And this line is called the critical line, and these are the, we have, as I've shown in the previous slide, this was the trivial zeros, and this strip is called critical strip, where all uh, the zeros of the zeta function are there. And we have proved in the previous slide that it is not defined for this point. Now this is the polar graph of the Riemann zeta function of half plus it. Now you can see a result given by Ramanujan, which was not proven by him. It was given to a letter to Hardy. It was written in that the sum of all these natural numbers till infinity is -1/2. We can prove this by the zeta function for real part of that when it's less than zero by using this functional equation. And by the Euler's definition of zeta function, we can write this as sum of the natural number. And by the functional equation for real part less than zero, we can write this as this functional equation. And by putting -1 here in this equation, we get this value and we get -1/2. Actually, I have it calculated here. This denotes the gamma function. Gamma function is the integral from 0 to infinity of the value e raised to the power x minus 1 times e raised to the power minus t dt. And here I using some calculus, I calculated the gamma of 1 as 1. Now we have a property in gamma function that the gamma of x plus 1 is x times gamma of x. Therefore, gamma of 2 is 1. And beta of 2 is pi square x by 2. This is using the Bessel's problem that we have discussed in the previous slides. And the sign of -5/2 is 1. And hence we can show that this is -1/12. And this is the prime counting function given by, actually the prime counting function and the function like this given by Riemann helps in just finding the zeros of the Riemann zeta function. And the the phi of x is actually a function. Means, for example, let's say phi of 10 means the prime numbers less than 10, the number of prime numbers less than 10, that is 2, 3, 5, and 7. That is 4 prime numbers are less than that. Therefore, the phi of 10 is 4. And it calculated a similar function like phi function called the j function, in which this was the function, and which he calculated, which was actually the same as the phi function. Actually, the phi function has the relation with the Riemann zeta function. So he at least wanted to know what any. Okay, sir. So this is the last slide. The question which I wanted to ask about Riemann hypothesis is that are there any functions which look like the Riemann zeta function such that they have the same properties like this function, like the zero lies on the critical strip between 0 and 1. The two examples which I found are this L function, which is 1 minus 3 to the power minus s plus 5 raised to the power minus n and so on. And this function was studied by Ramanujan, and this is and believed to have believed to have it has similar properties like the Riemann zeta function. And in this we can see an interesting property that this multiplied by this, and that is x square term and x3 term, we multiply and we get this term. And this is a property of this function. And this was my question, that this the function, are there any function which looks like Riemann zeta function? No, thank you, sir. And the $1 million prize is still up for grabs.
Yes, sir. Sir, is my screen visible? So, good evening, everyone. My name is Kanak Rade. I am in grade 5 and I study in school actually. While I was preparing for a few of the Olympiads, I came across the Pascal triangle. Initially, I thought it was a triangle of numbers uh, formed by adding the previous numbers. Eventually, when I started digging in, I came to know it had extensive application in algebra, number theory, and statistics. So, what is the Pascal's triangle? The Pascal's triangle is a triangular formation of numbers constructed by adding the two previous numbers above it. The very first and the very last numbers in any row will always be 1. It is full of patterns and secrets. The Pascal's triangle is infinite. It was named after the French mathematician Blaise Pascal. One topic he did not actually invent the Pascal's triangle, as it was originally invented by the Chinese mathematician Jian. He was given credit as he contributed in it a lot. Blaise Pascal was the first Westerner to put the number pattern theoretically. Features of Pascal's triangle. The row counting of Pascal's triangle starts with 0. The Pascal's triangle is often represented by an isosceles triangle. If we cut the triangle into half, both sides will show the same numbers. Outer line of triangle is always 1. The second diagonal of the line has consecutive positive integers. The third diagonal line has triangular numbers. This is how triangular numbers are represented. The fourth diagonal line has tetrahedral numbers. This is how tetrahedral numbers are represented. Reading the Pascal triangle. While reading the Pascal triangle, we start from the 0th row. And while reading a row, we start reading from the 0th position. Calculating of 2 raised to n and 11 raised to n. The addition of the numbers of each row is equal to 2 raised to n, where n is equal to row number. Example, if we take row 3, we have 1, 3, 3, 1. When we add them, we get 1 plus 3 plus 3 plus 1, which is equal to 8. 2 raised to n is equal to 2 raised to 3, is equals to 2 into 2 into 2 is equal to 8. The addition of numbers in expanded form of each row is equal to 11 raised to n, where n is equal to row number. Example, if we take row number 3, we have 1, 3, 3, 1. When we add them in their expanded form, we get 1000 plus 300 plus 30 plus 1, 1321, which is same as 11 raised to n is equal to 11 raised to 3 is equal to 11 into 11 into 11 is equals to 1331. Though there are few exceptions. The Sahoo triangle. When you shade in all odd numbers in Pascal's triangle in one number and leave the even numbers in another color, it makes Sahoo triangle. The Sahoo triangle is not just a work of mathematical art. It is also quite useful, especially when it comes to probability and calculations in the domain of combinatorics. Pascal's triangle in combination form. This is how the Pascal's triangle is shown when in combinatorics. Real life situations. Using Pascal's triangle to find probability and combination. Suppose you visit a shop to buy chocolates and you have 5 options. Then you got to choose 2. How many different ways are there? You can simply go by using Pascal's triangle. Visit 5th row, 0, 1, 2, 3, 4, 5, and second number 0, 1, 2, and you will get your answer. We say there are total 10 ways to choose 2 chocolates from 5 given options. Let us take one more example. There are 10 players and you got to choose 6 players from them. So for finding number of combinations you have to choose, let's go to 10th row. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and check 6th number. 0, 1, 2, 3, 4, 5, 6. Hence, there are 200 ways to choose 6 players from a total of 10 players. Finding shortest path using Pascal's triangle. Find the shortest path to reach from point A to point B, following the movements of each direction and not direction. So, using the Pascal's triangle, we can say that 1 plus 1, 2, 2 plus 1, 3, 3 plus 1, 4, 4 plus 1, 5. The same technique is followed for the second, third and fourth row. 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10 and 10 plus 5 is 15. 1 plus 3 is 4, 4 plus 6 is 10, 10 plus 10 is 20 and 20 plus 15 is 35. 1 plus 4 is 55, 5 plus 10 is 15, 15 plus 20 is 35 and 35 plus 5 is 70. Hence, there are a total of 70 ways to reach from point A to point B. There are many variations while doing these type of sums. Like you have to not cross a certain point or you have to only go through a point. Binomial expression. A polynomial equation with 2 terms usually joined by plus or minus sign is a binomial, like a plus b or a square plus b square. The numbers that form Pascal's triangle are binomial coefficients. Say you pull out the coefficients of the terms shown in red. You will discover that the coefficients form a triangle known as Pascal's triangle. Recent development. Pascal's triangle accounts for the discovery of new and often unexpected properties related to divisibility, binomial, construction and study of its fractals and graphs, and its application to important practical problems. Still, many fresh secrets are being revealed. Recently, mathematicians tried to expand further to below stated polynomial using Pascal's triangle. X plus y plus w plus z and so on raised to n. These are a few sites I referred while making this project. Thank you. Thank you. Thank you, sir. Yes, sir. Yes, sir. Yes, sir. Thank you.
I'm Swetanshu Sahoo of Class 5, studying in Delhi Public School, Bhilai. I would like to thank Chinta for the uh, opportunity they have given to present my research work. I chose net of solid as my topic. Ma'am, has it started? Yeah, I mean, ma'am, yes, yes, sir. Honored. Sir, can you see? Yes. Hi, everybody. Good evening. My name is R. Vijayakrishnan, studying in TS Senior Secondary School in Chennai. I am just promoted to class 5. Today, my topic is nets of solids and how can we use them to find the surface area of 3D shapes. What is a net? Generally, a net is a device made of fabric or rope used to catch things such as fish or butterflies. But in geometry, a net is a two-dimensional shape that can be folded to form a 3D shape or a solid. It can be vice versa too. A 3D shape can be opened to form their respective 2D shape. Let me give you a better example visually. Imagine a cardboard box opens. What do you see? A set of 6 rectangles or squares. Is it not? That is the net of the cardboard box, which is originally a cuboid or a cube respective. Let me show you. This is it. This is a cardboard box, which is originally a cuboid. If we open it, we can see 6 rectangles and 6 faces. How to find which shape does a net make? Net has the same number of faces as the solid. Net has the same shape as the face of the solid. Let us visualize this by using GeoGebra. This is a cube, and the other one is its net. The net has 6 faces as the cube, and it has the same shape, the square, which is in the cube. How do we find the surface area of a solid with its net? The surface area of a 3D object is the measure of the total area of all its faces. This means that one way to find the surface area of a solid is to find the area of its net. Let us see some examples. In this cube, I want to find the surface area of this cube with sides measuring 10 cm. The formula for finding the surface area of a cube is equal to 6a square. The surface area of a cube using formula is equal to 6a square, which is 6 into 10 into 10, that is 600 centimeters square. Now, how to find the area of the cube using its net? First, I am going to split the cube into 6 squares. Then, I am going to find the area of 1 square. After that, I am going to add the areas of 6 squares to find the area of the cube. Area of 1 square is equal to a square. Area of the cube using the net is equal to 6a squares. That is 600 centimeters square, which we got the same can be calculated using the formula. Let us see another example. A cuboid. The surface area of a cuboid formula is twice length into width plus twice length into height plus twice width into height. Considering length is equal to 5 cm, width is equal to 3 cm, and height is equal to 2 cm, the surface area of the cuboid is 60 cm square after applying the formula. Now, how can we find the area using its net? First, I am going to split the cuboid into 6 rectangles. After that, I am going to find the area of one rectangle, and then I am going to find the area of 6 rectangles. After adding that, we got 6 length into breadth. After adding the area of 6 rectangles, we get 62 centimeters square, which is the same when we calculated using the formula. What is showed are simple 3D objects, and we found their surface areas easily. Similarly, we can find the areas of prisms, pyramids, etc. using their nets. This is very useful as we do not need to remember complex formulae for finding surface areas. The simple way is to unfold the 3D object to its two-dimensional net and add the areas of all constituent shapes. Thank you. I wish to thank Chinta for giving me this golden opportunity, and I also wish to thank my parents and brother who helped for me to make this project. Thank you. Yes. Sir, but I have one doubt, sir. Yes, sir. I saw one. I saw other 3D shapes like triangular prisms, and it is difficult to find it is difficult to understand the formula of it. Yes. Yes.
Yes, ma'am. Yes, ma'am. Can you hear me now?
Thank you, sir.
This is my Sahoo of 5, studying in a public school, Bhilai. I like to thank Chinta for the support and opportunity they have given to prioritize research work. To the net of a short topic. Net of a introduction. Net is a two-dimensional of a shape which can be reorganized into the curve. The net of cube. There are 11 nets of cube. Difference between net of cube and the cube. Cube is a three-dimensional figure, but net of the cube is a two-dimensional representation of it. Similarity between cube and net of cube. Set of cube is made up of faces that are squares, and cubes have also faces that are squares. Function. The net helps us to visualize 3D figure. It helps us to find the place of a face in a three-dimensional figure. Thank you. Ma'am. Ma'am.
Thank you, sir.
Bye, sir. Thank you.
Thank
Thanks, sir.
Bye, sir. Thank you.